All right, everybody, welcome back to the next video. We are going to start an overview of the proof of semi-stable modularity. And we're going to begin by looking at residual Galois representations. So representations to GL2 of a finite field of characteristic P. And we're going to start imposing conditions on these representations that are going to be useful to us. We're going to look at two of the four conditions today. The first condition, condition A we'll call it, is the cyclotomic determinant condition. By the way, before I get into this, we are not going to quite be using Wiles and Taylor's original proof for Fermat's last theorem for our series of talks here. We're going to be using slightly improved, more streamlined versions of the proof that came out in the years following the original announcement of the proof. If you want to see the original proof of modularity from the semi-stable case, here are the two papers you need. Wiles, modular elliptic curves, and Fermat's last theorem, I'll call that W from now on. And Taylor-Wiles, ring theoretic properties of certain Hecke algebras, which I'll call WT from now on. Okay, let's go. Let's let P bigger than or equal to 3 be a prime. Let's let K be a finite field of characteristic P. Let's let rho naught be a Galois representation GQ to GL2 of K. So I'll call this a residual representation or a mod P representation from here on out. I'm going to start imposing conditions on rho naught that are going to be useful to me. They're going to be reminiscent of conditions that we saw that the Galois representations attached to elliptic curves in modular form satisfied on purpose. Here's the first condition. It's called condition A. I want the determinant of rho naught to be chi bar P. In other words, I want rho naught to have mod P cyclotomic determinant. Okay. So up next, we'll need some definitions. What's an ordinary representation? Well, let's see. Let's take a coefficient ring A. We'll say a Galois representation rho from GQ to GL2 of A is ordinary at P if the restriction of rho to the inertia group IP at P has the form a cyclotomic line and a trivial line. So it's upper triangular with a cyclotomic eigenvalue and a trivial eigenvalue. Okay, so this is a condition that only depends on the image of inertia at P. And of course, if the representation is residual, like let's say A is my finite field K here, I'll just replace chi P here by chi P bar. Okay, and I want this to be true, of course, for a suitably chosen basis. It's easy to see that if rho naught, for example, is ordinary at P, again, that means replace chi P by chi P bar in the definition, then any lift rho of rho naught is also ordinary at P. So as expected. We're going to also need to understand semi-stable representations. So what does that mean? I'll take a prime L. We'll say rho is semi-stable at L if one of the following is satisfied. Either L is P and rho is flat at P or flat at L if you like, ordinary at P or ordinary at L if you like, or both. So flat, ordinary, or both at the prime in question. Or L isn't P and the image of inertia at L is contained in the unipotent group. I say contained because the image of inertia could be trivial if rho is unramified at L, for example. So this star could be a 0. And again, I want this to be true for a suitably chosen basis. That goes without saying. Okay, and I'm going to say rho is semi-stable if rho is semi-stable at every prime. And this definition works for rho or rho naught, actually. Why is this called semi-stable? That's the next thing. Well, here's a kind of a key proposition. Let's call it proposition 1. Let P be a prime. Suppose E over Q is an elliptic curve, and suppose E has semi-stable reduction at P. Then rho EL and rho bar EL, the L-adic and mod L representations attached to E, are semi-stable at P for all primes L. I've actually already given you enough information to prove this. There is a section in my notes in chapter 1 called Local Facts about rho EP and rho bar EP. Chapter 1 of my notes, previous video. Go check those out. See if you can prove this very easily from those facts. In fact, those facts let me be more specific. I can say that if E has good reduction at P, then rho EP and rho bar EP are flat. And I can say that rho bar flat at P, I should say. And rho EP is ordinary at P if and only if rho bar EP is ordinary at P, if and only if E has either good ordinary or multiplicative reduction at P. Again, all of this follows from those local facts. Here's an interesting fact that we won't need, but it's very deep. The converse to the proposition is also true in the following sense. If rho EP is flat, respectively semi-stable at P, then E has good, respectively semi-stable reduction in P. This is a much harder fact. You can find the proof of this in Saito's first book, Fermat's Last Theorem, Basic Tools, page 103. You need to understand group schemes, finite flat group schemes, étale group schemes pretty well. You need to know your algebraic geometry pretty well, and you need to understand the basic theory of neuron models of elliptic curves, which we'll be talking about later in some, but not too much detail. Okay, why am I bringing up all these definitions? Because here's the second condition I want to put on my residual representation rho naught from the beginning. I'll call it condition B. Very simply, I want rho naught to be semi-stable. Okay, and so starting next video, we'll look at the other two conditions that we want to impose on rho naught. And thanks for watching, and I'll see you then.